All right, we're back around page 7 of note 16. We're talking about parametric equations. So we talked about various slopes, dx dt, dy dt, dy dx, various rates of change, I guess I should say. So dx dt is left, right, dy dt is up, down, dy dx is a slope of a tangent line. Usually it's a function of t. We talked about the second derivative, which is definitely the most complicated of those to calculate. It's the derivative of dy dx with respect to t divided by dx dt. Why are you dividing? Chain rule, right? Dy dx is a function of t, so to get the derivative with respect to x, we have to chain rule it. And it works out really nicely, and you should definitely memorize that and never forget it. So it's definitely like a multiple choice type thing for sure. And I've never seen it on the calculator section, but like, why not? Next thing we're going to talk about is arc length. So arc length is really a common question for parametrics, because when you talk about parametrics, you talk about a thing literally following the path of the parametrics, right? So with my pointer, we could have something, if we had parametrics for this curve, something is literally following this curve, which means that the length of this curve is exactly how far it traveled. So we need arc length in parametrics because it corresponds directly to distance traveled. So we're going to need to know it. This is the formula. So it's the integral from a to b of the square root of, and then it's f prime of t squared plus g prime of t squared, or if you prefer, dx dt squared plus dy dt squared. Now I just want to show you something. We did arc length for a function. I'm going to mess around with this for a second here. So let's say we do. I'm going to factor dx dt squared out of both. So dx dt squared out of both leaves me with 1 plus. If I do dy dt squared divided by dx dt squared, that is dy dt over dx dt squared, but dy dt over dx dt is actually dy dx squared, then dt, and then this, well, this, the square root of dx dt squared, I'm taking some liberties here, but I think they're okay liberties to take, is 1 plus dy dx squared times dx dt, but dt, this can be dx squared dx. It's the arc length formula for a function. Look at that. They're basically equivalent, which I always think is really neat. I like to, mismatched parameters. Mismatched delimiters, I think is what that's called when you're trying to like, when you're getting debugged and it yells at you. So they're equivalent, and that's like a really neat thing. So you can remember one, you can definitely remember the other. I would say this one is, I would say this is more useful, but you know, whatever. So let's see if we can find the circumference of this circle. This is actually a pretty common, so these are the parametrics for a circle that has a radius of a. So I'm going to find dx dt, which is negative a sine of t. Find dy dt. So you got to find both of those so that you can plug them in. Cosine t. So we're going to do the integral from 0 to 2 pi of the square root of dx dt squared, a sine of t, and then dy dt squared, a cosine of t squared, and then dt. So that's the integral of the square root of, I'm going to just take out the a squared right now, a squared, and you get sine squared plus cosine squared. I don't know if you saw me hesitate before I didn't put the parenthesis. I was like, I don't want to put it, but I also don't want to not put it. dt. All right, what do we got here? Well, sine squared plus cosine squared is our favorite thing. It doesn't come up enough. You know, it's 1. This is 1. So this is the integral, bounds. Mind your bounds, man. This is the square root of a squared. dt squared, a, well, a is, I guess, greater than 0. So we're going to say this is, oh my God, 0 to 2 pi of a dt. So that's at from 0 to 2 pi. That's a 2, which is 2 pi a. Well, does that make sense? It does. If this is a circle with radius 2, Therefore, the arc length all the way around the circle is 2 pi r equals 2 pi. Where did I get 2? Radius a. So 2 pi r would be 2 pi a. So we got it. So the arc length formula gave us the circumference of a circle. That's a really cool idea. I like that. So let's see what we got left. All right, I'm going to do, how long do we think this question is? Find the particle's position, find the distance traveled. I don't think it's super long. I'm going to potentially do both of these here. Set up but do not evaluate an integral for the length of the path described by the parametric equations. X is 1/3 t cubed and y is 1/2 t squared between 0 and 1. All right. So dx dt is t squared. dy dt is t. So we're doing the integral from 0 to 1, square root of. So remember, those are our t bounds because it's dt. They're not the x bounds. Common mistake. Dx dt squared is t to the 4th. Dy dt squared is t squared. dt. So this, it says but do not evaluate, but like, you know, I think we could do it. So t is between 0 and 1, so t is always positive. So you take t squared out of both, and then square root of t squared is that. And t squared plus 1 dt. This, you need a 2, and so a 1/2, and then 2/3, I think. So I think you get 1/3. So here's what I'm doing in my head. I need a 2 here, so a 1/2. And then it's to the 1/2. So plus 1 is 3/2, so 2/3. 2/3 and 1/2 give you 1/3. And then t squared plus 1 to the 3/2. And then between 0 and 1. So like, you could have evaluated that. There's no reason not to evaluate it. But anyway, it told us not, it expressly told us not to. And I expressly ignored that. Also, once you get here, watch out, because people are always thinking when you plug in 0, you get 0, because that happens a lot, but that's not what happens here. This is 1/3, and then you get 2 to the 3/2 minus 1 to the 3/2. So there's a little more to it there. Don't just think because 0 showed up, you're going to get 0. Okay. A particle moves along a path described by a set of parametric equations such that dx dt is that beast. I don't know. This has no simple antiderivative. This needs to be a calculator question if you're going to like find things. And then y of t, not dy dt. Y of t, the actual y is shown on the graph below. That's interesting. At t equals 0, we know that the position of x is 5. Yeah, all right. So x of 5. I'm going to do it up here and then move it down. What am I doing? X of 2. X of 2 should be x of 0 plus the integral from 0 to 5 of, I'm going to say x prime of t dt. I believe that the notation is common enough that you don't really need to like stipulate, but you could say this is x prime of t if you want. So this is calculator, and I'll do that on the calculator. And then y of 2 is, you can not just read it off. I mean, you can almost just read it off. What is the slope? You go up 5/3. Okay, so this equation is, there's this new arrow thing. Let me try to do it. I'm not like super good at it because I think I don't like, that's supposed, all right, hold on. There, look at that. Isn't that a nice arrow? What I'm not good at is it. Like, something about it. Oh, and then I can't, I thought it would let me like play with the, I can. Okay, hold on. It's like all I want to do is make my notes look awesome. How about that? All right, so sorry you had to watch that. This equation right here is like y equals up 5, so 5/3 x minus 3. So if I plug in 2, y of 2 is going to, I guess this is technically y of t, right? Because, so y of 2 is going to be 5/3, 10/3 minus 9/3, 1/3, which like I probably could have just guessed, but you don't want to just do that. So oh, let's do 5/3 to -3, which was what? 1/3. Okay, so we got to use a calculator to find x. I will do that in a minute when I see what the next question is. So this will be something, and then we'll write the ordered pair. Distance traveled on 0 to 4. Okay, there's an issue with this. So dy dt is like a piecewise function, right? Because this is the graph of y as a function of t. This is not dy dt, which means that y prime dy dt is piecewise. It's the slopes, right? So this we said was up 5/3. That's 5/3 for 0 to 3. And then down 3/3. That was a hard way to get to -1 between 3 and 6. So that's a fact. And I need that because dx dt is always the same. So I need to do, the distance traveled will be the integral from 0 to 3 of the square root of, I'm just going to write it out like this. And then on the calculator, I'll be a little more careful. 3 to 4 of the square root of x prime of t squared plus y prime of t squared dt. Okay, so now it's calculator work. So I'm going to do the calculator and then get out of here. Let's see. So new share, calculator, here we go. That's from the previous problem. All right, so what am I doing? I'm gonna store dx of t, which is usually how I store like x prime for parametrics. It's inconsistent with how I do it for like regular functions, so I don't know, I should get on the same page about that, but I'm not. So I want to do 5 plus the integral dx of t. T is a variable going from 0 to 2. We get that. So I'm going to write that down, 12.194. And then my ordered pair I'm also going to write. So at t equals 2, 12.194 comma 1/3. This is not super unusual to have like multiple representations of like the function and the derivative and all kinds of stuff, because you need to be able to work back and forth like fluidly between them. So arc length, I'm going to do the integral from 0 to 3 of the square root of dx of t squared plus, the first one is 5/3 squared dt. I'm just going to press enter just to like make sure I did it right. And also so that I can do this, just like change it and go from 3 to 4, but then I need to change from a slope of 5/3 for y to a slope of -1. So strange, -1, and get that. So I'm really doing this plus this. And I get 55.393. So I'm going to write that down. Approximately 59.393. All right, I will go back to the notes so that you can see them, but I think we did an okay job here. We either did a good job because we got it all right, or we did an okay job because I think our explanations and thought process are correct, but maybe we messed something up. But what a nice arrow, right? That's my takeaway. Also, did I do this entire page? I don't even remember. I don't know if this is video 1 or video 2, but here you go. We get this. All right, so I'm gonna wrap it up and I will see you in the next video. No idea what we're doing, but see you there.